To what extent can science concentrate energy capable of altering the fate of a region in seconds? We will unravel, with rigor and in dangerous detail, the physical principles, historical evidence, and manufacturing processes that accompanied the birth of thermonuclear weapons. I will tell you how science and ethics intertwined in a race that forever changed global security. Extraction and preparation require global operations, massive facilities, and extreme measures against radiation and espionage. Let's start with uranium, the basis of primary fission. It is extracted in remote mines where giant excavators remove tons of earth to obtain pitchblende, a shiny black mineral containing uranium. The ore is then ground into a fine powder and treated with strong acids to dissolve the uranium and separate it from impurities. The result is a yellow concentrate called yellow cake, similar to flour but highly radioactive. The problem is that natural uranium is almost entirely uranium-238, which does not fuse easily. Less than 1% is uranium-235, the bomb-using isotope. Enriching it is an art, a process that consumes as much energy as an entire city. Enrichment is done in enormous plants with thousands of centrifuges, tall tubes that spin at supersonic speeds, faster than the tip of an airplane propeller. Hexafluoride gas is injected into the reactors, and centrifugal force separates the isotopes. Uranium-235, being slightly lighter, migrates. This cycle is repeated in decentrifuge cascades for months until 90% purity is reached for weapons grade. It is tedious and expensive work, and not without risk. As an interesting aside, during the Cold War, the Soviet Union built entire cities dedicated to this, such as Pripyat near Chernobyl. Although that plant was for energy, not bombs, it illustrates the industrial scale involved. Then there's plutonium, another fundamental fuel for primary fission, but unlike uranium, it's not mined but produced in nuclear reactors. To make it, uranium-238 is used, which is exposed to a constant flow of slow neutrons inside a reactor, such as those at Hanford in Washington, D.C., a key site in the Manhattan Project, where large amounts of cold water were circulated to cool the fuel rods. When uranium-238 captures a neutron, it temporarily transforms into uranium-239, which then decays into neptunium and finally plutonium-239. After several months of irradiation, the rods are removed and dissolved in tanks of hot nitric acid, a process that releases toxic fumes and requires powerful ventilation. The plutonium is separated using organic solvents in a method similar to filtering gold from a chemical solution. The result is a silvery grey metal that feels warm to the touch due to its own radioactivity. When it comes to fusion materials, deuterium and tritium are the key players. Deuterium, known as hydrogen-2, is present in seawater in very small quantities, approximately 1 part in 6,000. To extract it, heavy water is produced in specialized plants such as those in Canada, where electrolysis separates the water into hydrogen and oxygen, prioritizing deuterium. This process is slow and requires thousands of liters to obtain just a few grams, but it's fascinating because deuterium is stable and abundant in the ocean, reminding us that fusion fuel is practically everywhere, although its extraction is expensive. Its historical significance is such that during World War II, the Nazis attempted to produce heavy water in Norway for their nuclear program, but Allied commandos sabotaged the plant in an operation that sounds like something out of a spy movie. Tritium, or hydrogen-3, is much harder to come by. It doesn't occur naturally in useful quantities, as it decays with a half-life of 12.5 years, transforming into helium-3. It is produced by bombarding lithium-6 with neutrons in special reactors. Lithium, in turn, is extracted from extensive salt flats in the Atacama Desert, Chile, or in the Salar de Uyuni, Bolivia, where evaporated lakes leave deposits rich in this metal. After purifying it to isolate lithium-6, which represents only 7% of natural lithium, it is placed in targets around the reactor core, where neutron capture generates tritium and helium-4. The gaseous tritium is then extracted by heating and purifying this radioactive material, which even emits a faint glow due to its own beta decay and is also used in luminous clocks. Its rarity is remarkable. There are only about 25 kilograms of tritium available for nuclear use worldwide. Furthermore, its constant decay requires constant repositioning of arsenals, posing a huge logistical and economic challenge that has cost countries like the United States billions. With deuterium and tritium ready, deuteride is manufactured. In controlled atmosphere laboratories, lithium-6 is combined with deuterium under high pressure and temperature, resulting in a stable, white and easily molded powder. This choice is not accidental. During detonation, neutrons transform the lithium into fresh tritium at the same instant of the reaction, maximizing yield. This material marked a before and after the fourth Mike test, as it allowed the design of compact and practical weapons, replacing bulky cryogenic systems. A clear example was Castle Bravo in 1954. A calculation error increased the power from 5 to 15 megatons, spreading radioactive rain over nearby islands and the Japanese fishing boat Lucky Dragon, causing an international incident that even inspired the first Godzilla movie. The complexity increases with other strategic materials. Beryllium, a light metal mined in Utah or Brazil, coats the outer structure for its ability to reflect neutrons, retaining them in the core to improve efficiency. Handling it is dangerous. Prolonged exposure can cause berylliosis, a serious lung disease. High explosives, such as HMX, are produced in specialized plants. These mixtures are capable of detonating at several kilometers per second, and high-density polystyrene foam, similar in appearance to disposable cups, is used between the inner layers. This foam converts X-rays into plasma during the explosion, ensuring more efficient energy transfer between stages. With all the materials ready, assembly takes place in fortified bunkers. Places like Los Alamos in New Mexico, where the arid desert conceals underground complexes, or Osarov in Russia, a closed city dedicated exclusively to nuclear physics. In these environments, scientists in protective suits work alongside high-precision robots to avoid any risk of contamination, while monitoring systems detect even the smallest radioactive particles. Booster is installed inside. This technique amplifies the reaction by releasing additional neutrons through a mini-fusion. Its effectiveness was demonstrated in 1951 during Operation Greenhouse, a series of tests in the Pacific that confirmed key principles of modern thermonuclear weapon design. Around the central sphere are placed lenses of chemical explosives, curved blocks calculated with mathematical precision to generate a perfectly spherical shockwave. Its function is to compress the core evenly, as if squeezing a sponge from all sides at the same time. The electric detonators, synchronized to the nearest nanosecond, are connected by extremely thin wires. The entire assembly is wrapped in a reflective layer of beryllium. Before it is fully assembled, preliminary X-ray tests are performed to check internal alignment and ensure there are no defects that could cause a fissile, i.e., a weak detonation. In the transition to the secondary stage, a tough tubular uranium-238 cylinder is fabricated and filled with densely packed layers of lithium-6 deuteride pressed under extreme hydraulic pressure. A thin plutonium rod known as a spark is inserted into the center of this cylinder. Plug or spark plug, whose function is to initiate an internal fission at the exact moment when the compression reaches its critical point. This cylinder is vacuum sealed to prevent oxidation, as even minimal corrosion could compromise the reaction. It is then placed directly beneath the primary charge, separated from it by a layer of polystyrene foam injected with millimeter precision. The entire warhead is conically shaped to fit missiles and coated with a layer of beryllium. Inside, crucial electronic systems are integrated, along with altimeters that measure atmospheric pressure to detonate at the optimal altitude, impact fuses as a backup system, and special batteries that are activated by the heat generated during re-entry. In extreme designs such as the Soviet Tsar bomb of 1961, the most powerful ever detonated at 50 megatons, enormous tertiary stages were added. These consisted of scaling the cylinder with uranium or lead to reduce radiation. This modification prevented an even greater environmental disaster, but the explosion still generated a fireball 8 kilometers in diameter. Final assembly takes place in clean rooms, where the air is continuously filtered, and each part is assembled with precision down to the micron. To validate the design without resorting to actual detonations, a requirement since the 1966 Comprehensive Nuclear Test Ban Treaty, computer simulations on supercomputers capable of modeling the behavior of each atom are used. In this context, a striking historical fact emerges. Edward Taylor, one of the driving forces behind the Taylor-Ulam design, along with Stanislaw Ulam, who contributed the key idea of radiation compression, testified against J. Robert Oppenheimer in 1954, which contributed to his security clearance being revoked. With the bomb ready to detonate, its operation is like a perfect choreography that occurs in just microseconds. As it descends aboard a missile, a sensor detects the optimal altitude and sends an electrical signal that activates the chemical explosives in the primary stage. These explosives generate shock waves that implode the plutonium sphere, compressing it to a critical density. At that instant, fission begins. Neutrons split the nuclei, releasing intense X-ray and gamma-ray radiation. The boosting system injects a mixture of deuterium and tritium, which fuses slightly to generate even more neutrons, multiplying the power of the reaction. X-rays traveling at the speed of light impact the foam surrounding the secondary stage, transforming it into an extremely hot plasma that compresses this second payload before the physical shock wave arrives. It's a perfect game of timing designed to prevent the detonation from occurring prematurely and thus maximize its destructive power. What this process demonstrates is not just a scientific breakthrough, but a chain of decisions, political, military, and economic, that transformed knowledge into instruments with far-reaching human and environmental consequences. The lessons are clear. Science alone does not determine destiny. The policies that govern it, the mechanisms of international oversight, and the public will to demand transparency and accountability do.